Happy Friday, everyone. Welcome back to the continuing saga of our Back to Basics series with Distortion, Signal Leakage, Codewords, and more. Did you know? Part 2. I'm your host, Brady Volpe, founder of the Volpe firm and now Chief Product Officer of OpenVault, here to guide you through the captivating labyrinth of DOCSIS. As always, I'm delighted to be accompanied by our esteemed guest, presenter, and cable industry stalwart, Ron Hranac. If you joined us for the last episode of Did You Know DOCSIS, Back to Basics and Clearing Misconceptions, you'll know we're all about diving deep, dispelling myths, and demystifying complex topics in the DOCSIS world. We're also about challenging your existing knowledge because who knows, maybe there are some things you'll think you know, but, well, you might be in for a surprise. In this episode, Ron will lead us through an impressive range of topics. We'll discuss both analog and digital distortion, unravel the meaning of code words, demystify signal leakage, explain ingress, touch on Amplifier AGCs, learn about frequency response, and much more. It's sure to be an enlightening and informative ride. So as always, Ron needs no introduction, but be sure to check out his extensive bio in the description below. Without further ado, let's dive into today's topic with the incomparable Ron Hranac. Ron, it's a pleasure to share the virtual stage with you once again.
Thanks, Brady. It's a pleasure to be here. Always have a fun time doing these sessions with you. I know you and John focus more on the DOCSIS side. I like to focus more on the RF side. As I tell people, I can't spell IP, but then I know DOCSIS people who can't spell RF. So I fill in the blanks for the RF side, and a lot of it is applicable to DOCSIS, and a lot of it's just applicable to general things in general. So thanks again for the introduction. My pleasure to be here. And a word of warning for those of you who are either watching this live or watching the recording after the fact, you're likely going to hear the grandfather clock chiming from time to time in the background. That's not meant to be an alarm or anything. I've temporarily moved up to the dining room in my house. Our dog just had knee surgery, so my wife and I are taking turns watching him. So that's why I'm doing this. So let me punch up the share screen button here. And let's see, it says got to click this, got to click this, got to click that.
And best wishes to your dog there as he heals up.
Thank you. His name is Luke, named after the Jedi.
Yes.
As you would expect from me, I think. Anyway.
You are his father.
Oh, yeah. I am your father. So anyway, we don't want to go down that route. So today, as Brady said, it's a discussion about Did You Know Part 2, and this session includes a whole bunch of topics that continues where we left off last time. I've got a link to the YouTube recording at the end of this presentation where you can watch the Part 1.
Yep.
If you did not.
We also have Part 1 in the description below for anyone who missed Part 1. Be sure to catch that one.
There is a test, so you must watch it.
Yes.
All right. So why don't we go ahead and get this underway? And I want to start by talking about distortions. Those of you who've been in the cable industry any length of time and have worked in the outside plant are very, very familiar with distortions that can happen in cable networks. And of course, distortions are a normal byproduct of the way active devices such as amplifiers and even fiber nodes work. We can't avoid them. They're still there. In cable networks that are carrying a lineup of analog TV channels, they have a real widely known characteristic as clusters of little beats that appear under the visual carrier or on either side of the visual carrier. And those distortions include second order distortions and third order distortions. They're called composite distortions, or more specifically composite triple beat, or good old CTB, composite second order, CSO, and even common path distortion, or CPD, that happens in our return path. When the industry started migrating away from the carriage of all analog TV channels and adding single carrier QAM channels to the network, a lot of people thought, incorrectly, unfortunately, that, hey, the distortions went away, that we don't have CPD anymore, we don't have CSO anymore, and even common path distortion went away. Well, no, those distortions did not go away. They just took on a different look. They actually look like wideband noise. So we don't see these clusters of discrete beats around the visual carrier of the analog TV channels anymore in an all digital network. Well, first of all, there aren't any analog visual carriers, but those beat clusters that we were used to seeing in the old days have changed. So they look different. They actually look like noise. And it's pretty easy to confuse those noise-like distortions with thermal noise. We're going to get to that in a second. But the distortion products, that would be the digital version, if you will, of CPD and CSO and CTB. We call them by any number of about 2 or 3 different names. And these are all legitimate names, but composite intermodulation noise, or CIN, composite intermodulation distortion, CID, or intermodulation noise, IMN. I think CIN is probably one of the more common names that's used, but all 3 of these names are accurate. And again, don't confuse these with the thermal noise in our networks, which we're used to measuring when we do a carrier to noise ratio measurement. So I say don't confuse the two, but
yeah, and I would agree. CIN is the most common one that I think I tend to use, and I hear other people using.
Yeah, I think that's probably the one that I see most widely used as well. But that refers to the noise-like distortion. And I say don't be confused about this. Unfortunately, confusion reigns, and it reigns supreme. Now, here's the interesting thing. Those of you who have monitored a spectrum analyzer or an instrument that is capable of measuring things like carrier to noise ratio while you're tweaking signal levels at amplifiers out in the plant, you know that as you crank up the RF levels in a cable network, the carrier to noise ratio, or CNR, gets better. So you've got the noise floor here, and you crank up the RF levels, and the carrier levels get higher and higher, and the carrier to noise ratio gets better and better, which is normal behavior. But if you got a lot of digital signals, you keep cranking up those RF signal levels, and the carrier to noise ratio will improve for a while. And then all of a sudden, you reach a point where the noise floor starts to go up, and you say, wait a minute, how the heck can the noise floor increase and the apparent carrier to noise ratio get worse?
Not what we expected at all.
No, it's not. It's counterintuitive. You think, wait a minute, is there something wrong with my test equipment? Am I reading this wrong? The answer is no. And the reason why is that noise floor is no longer just thermal noise. It's now a mix of thermal noise, the N in carrier to noise ratio, and those good old noise-like distortions, or CIM. So when we characterize the cable network in the presence of CIN, the term carrier to composite noise ratio is very commonly used. So no longer do we just call it a plain old carrier to noise ratio measurement, even though we make that measurement the same as we did for traditional carrier to noise ratio measurements. But it's just the CCN ratio is a much more appropriate metric because it takes into account the effects of both carrier to noise ratio and carrier to that noise-like distortion ratio. And if you look at a spectrum analyzer similar, you see that noise floor coming up, you can't visually discern the difference between the thermal noise and the distortion noise-like impairment, the CIN. Well, that is not unless you go back and turn off all but maybe 1 or 2 channels in the network so that the distortion goes away, and then what's left is your thermal noise. But right, that would be somewhat...
Thermal noise and distortion on any type of device we're going to look, they just look the same. So that's why you're saying you can't tell the difference between them.
You can't tell the difference between them, not visually anyway. So be really service disruptive if you went back and shut off most of your channels. You could say, all right, the noise floor went down.
We fixed the noise. Good news is we fixed the noise. Bad news is all of our subscribers are offline.
Yeah, that's not a good thing. So anyway, so here's a graphic representation of what's going on. And let's, I punched that too far. So let's go back to the distortions in an all analog TV network. So this graphic here shows the thermal noise floor, that solid green line that goes horizontally across the screen. And then the vertical spikes are the analog TV channel visual carriers and sound carriers. And you can see that in that situation, the composite triple beat, which is a third order distortion, falls directly underneath the visual carriers. And the composite second order distortion, or CSO, falls either side of it. I show it, I think, about 1.25 or maybe 0.75 megahertz. But CSO can appear in those clusters either at plus or minus 0.75 megahertz and plus or minus 1.25 megahertz. But I just show the upper and lower just to keep it simple. But that's where those beat clusters are, and they're composite distortions. So for each dB that you crank up system levels, the composite triple beat ratio gets worse by 2 dB. Now, I know some people say, wait a minute, composite triple beat, I've heard that things get worse by 3. Well, no, the ratio degrades by 2, but the distortion itself will change by 3. So you crank the levels up 1, the distortion ratio gets worse by 3, but the difference increases by 2, gets worse by 2. Composite second order ratio, and I understand this is the ratio, degrades by 1 dB, and the carrier to noise ratio gets better by 1 dB. So that's what happens when you crank up levels by a dB.
And that means third order distortions are actually more detrimental to our network than second order distortions. Is that correct, or is that not correct?
I'm going to say there's some it depends there. The second order distortions can do some very, very strange things, and in networks with long cascades, we don't see those much anymore, but there's still a few of them out there. But in long cascades, you can actually, in some cases, see the composite second order distortion products kind of breathing. That is, getting better and getting worse over time. Or you might see that you go from one amplifier and make a CSO measurement, and then go to another amplifier down the cascade and say, wait a minute, it got a little bit better. And it has to do with the complex phase relationships in those second order distortions. There's a discussion about that in the SCTE math document. That's SCTE 270 2021, available on the standards download page. There's a real good write-up about that in that math document that explains why that happens.
And thank you for addressing that. While you're here, Ron, I don't know if you'll cover this later or if it's a good time to talk about it right now, but isn't there always a trade-off between CNR and CSO and CTB, or these distortions?
Yeah. There's a window, and you've got to kind of find the sweet spot in amplifier operating levels versus distortion performance. And the longer the cascade, the worse that window gets, which means it doesn't take much tweaking to make things really wonky at the end of a long cascade. If you've got a cascade of 40 or 50 or 60 amplifiers, things can get real bad in a hurry. Yeah. So you've got a very, very carefully managed level. So that's a really good point, Brady.
But it could even be a cascade of 4 amplifiers where, you're, and you alluded to this earlier, where we think, well, just, more is better. Let's get the CNR as good as we can get it. But to your point, as you get that CNR really high, then you're going to get your distortions bad. And that's where you get the CIN getting bad. So, to your point, as we continue to get this, as you continue to get the CNR better, your CIN is going to get worse. And that's where you're going to see your noise floor get really bad. So we have,
no, go ahead.
I was just going to say, we had a question here from Jeremiah that I think is along that same train of thought. He's saying, is it safe to say that there's more potential composite with CSO versus CTB?
I'm going to say that the composite triple beat has more beats. And this is one of those trickier questions, and you start to get into some gnarly mathematics. But if you look in some of those little pocket technical guides, some of the vendors included distortion charts, and the charts showed the number of individual beats in a given beat cluster on different channels in the spectrum with a certain channel loading. What, of course, changes is the amplitude of those, or the magnitude of those distortions, but the numbers are related to the total number of channels in the cable network. And you can have underneath, say, a visual carrier in the middle of the spectrum someplace in all analog network, the CSO beat, which is, it's just this little hump under the visual carrier, but there are going to be 1,000 or 1,500 little individual beats in there. And then that tends to change count somewhat over the spectrum. And it tends to be, as I recall, worse for the CSO count-wise. But both of these types of distortions can have a pretty negative impact on analog picture quality. But it's a trade-off with respect to levels. And in the case of an all analog network, it's the same thing. It's all right, where do you can get really good carrier to noise ratio performance by cranking the levels up, but as you continue to crank the levels up, the distortions get worse. And eventually you reach a point where you start to see an impact on picture quality in an all analog network. Most of the amplifier manufacturers have done a good job over the years of characterizing their amplifiers in a lab. And then what they do is they will publish distortion performance numbers on the spec sheets, and it'll say for X number of channels at these signal levels, this is the distortion performance. And then you can use that published information and adjust it with some formulas to match your actual channel loading and your actual signal levels in your network. And that's something that engineers have done in cable networks for decades. It's pretty important. And it also points to the importance of properly aligning the active devices in the plant, whether it's the nodes or the amplifiers or both.
And there's the 12:15 bell. Thanks for the comment, Jeremiah. Thanks for the answer, Ron. And for everyone who's listening, please do drop your questions into the comment section or the live chat. If you're watching live, please do subscribe, like, and hit the notification bell. We'd really appreciate that. And continue on, Ron. Thank you so much.
And continuing on, here we have a combination that was pretty typical as the cable industry was starting to add digital channels to their networks in, I'll say, the 90s and later. And this would be the case. We're up till even a few years ago. We have a mix of analog and digital signals in the network. And here you can see that you still have the beat clusters, the CSO and CTB beat clusters, represented by the little black vertical lines underneath the visual carriers. But note that here we have the green line, thermal noise, as before, but we also have the digital noise-like distortions by this kind of represented by this kind of reddish colored line. And then the purple line up at the top is the mathematical combination of the thermal noise and the composite intermodulation noise. And you can see that it's noise-like, but you've also still got some of the I'll call it the traditional looking second and third order distortions. So here, things start to get a little interesting as you play with levels. So for each 1 dB increase in system carrier levels, the CNR, CTB, and CSO ratios behave as they did with all analog operation. The CIN ratio, that's remember, this is the reddish line there, degrades by 1 to 2 dB for each dB increase in signal levels. And that's because it's a mix of second and third order distortions. And then the CCN ratio, this is the purple line, that's the mix of thermal noise and CIN. That degradation depends on the CIN and CNR values.
Right.
And then finally, in an all digital network, which is what many cable networks are these days, you don't see any of the old legacy looking distortions. Now what you've got is the thermal noise represented by the green line, the composite intermodulation noise represented by the reddish line, and the composite noise represented by the purple line. So here, for each 1 dB increase in carrier levels, the CNR behaves as it did with all analog operation. So carrier noise ratio gets better by a dB. But the CIN ratio here degrades by 1 to 2 dB, again, because if it's a mix of second and third order components. And the CCN ratio degradation, as before, it depends on the CIN and CNR values. And here it's, I think, helpful to work with the manufacturer of the active devices because they can oftentimes provide you with some guidance on how their particular equipment performs because they'll do extensive lab tests. And I know that when I worked on the vendor side of the business, cable operators would come to the corporate labs and do testing in the lab environment with their channel loads, the number of channels they had, the bandwidth, and the channel types. And that way they could actually get some good characterization of what the active devices were doing in a cascade over temperature. So I think that's something that the manufacturers are really well positioned to help out with.
Yeah, so we have a question here from Charlie Moz. He says, comment, design your transmission system to hit peak NPR, and I'm not sure if we've covered NPR, noise power ratio, at minus 3 dB, and it should be a good /safe /starting point to optimize for noise contributions against SNR. So I think he's basically saying, so you're and Ron, you may want to talk about your noise power ratio, but it's that's like your curve that determines where the manufacturer's curve to determine where the ideal point is to run your amplifiers. And he's basically saying back off 3 dB where the peak is from your noise power ratio. So I don't know, Ron, do you have any guidance or suggestions around that being a good starting point?
Well, I don't have a slide in the deck on NPR, and I've thought about including it. I do have a presentation on NPR that's separate from this one, and it's not part of a Did You Know? It's just a standalone short presentation on NPR. Traditionally, the cable industry has used NPR or noise power ratio to characterize the performance of upstream amplifiers and fiber optic links. And we've been doing that for a long time. And he's right. And in that case, what you want to do is typically back off from the peak a bit 3 dB, and the amount can vary. There's a good paper that I co-authored with Don Sorensen and Frank Eichenlaub back in 2008, or I think it was 2008 for SCTE, and we talked about that, and we recommended using a BER dynamic range curve and overlaying it on top of an NPR curve, and then having the operation, that is the power going into the laser, not quite dead center in the BER curve, but slightly, I think if I remember right, we were saying slightly to the left of that, which would provide optimum performance. And if you looked at it on an NPR curve, it was down from peak a few dB for good performance. Industry hasn't really used NPR much in the downstream until very recently.
Yes.
And in that case, cable operators that are evaluating 1.8 gigahertz amplifiers are finding that things behave a little bit differently than we're used to, particularly with the channel loads and the total composite power numbers that are being seen with 1.8 gigahertz amplifiers. And there's a good article in Broadband Library, and I think it was also part of a paper or presentation by Deanna Linton at Charter. And she talks about, she's a corporate engineer in Charter Labs, and she talks about using NPR measurements in the downstream to characterize 1.8 gig actives. So do some digging through Broadband Library's archives and look for Deanna's really, really well done article. It's very informative.
Excellent. Good recommendation. Thanks, Ron.
Okay. All right. So let's continue with the Did You Know? And we've talked about this in the previous sessions, but it's always good to repeat it. Did you know that dBmV expresses power in terms of voltage? We tend to look at that and say, well, wait a minute, MV is millivolt. Isn't that a voltage reference? And it is, but the decibel by definition is a ratio of two power levels. So we're actually expressing power in terms of voltage. So what's called the 0 dB reference for decibel millivolt, 0 dBmV, equals 13.33 nanowatts of power. That's 13 billionths of a watt. And then we further define that as 1 millivolt root mean square across an impedance of 75 ohms. So what that means is then at 1 millivolt in 75 ohms impedance equals 13 billionths of a watt, or 13.33 nanowatts. And that's what we call 0 dBmV. So that's power in terms of voltage. And then when we make a measurement in dBmV, we're actually measuring other levels relative to this so-called 0 dB reference. And the formula for that is dBmV equals 20 times the base 10 logarithm of the ratio of some level, whatever it is, in millivolts divided by 1 millivolt. And for those of you who are curious about the decibel and haven't seen the earlier presentations, go back and watch the one on the decibel primer that we did a while back. That's a really good one. And also the one on signal levels.
Yeah, that was an excellent show we did. So I'll put a link that into the show notes as well, Ron. Thank you.
Great. That's great. Thanks, Brady. All right, let's talk a little bit about signal leakage in an all-digital network. Did you know that leaking digital signals can cause harmful interference to over-the-air services? Now, when cable operators started carrying digital signals in and near the VHF aeronautical band, the thinking was, well, it's not going to be a big deal if a QAM signal is leaking. It's noise-like, and since we typically measure the leakage power in a very, very narrow bandwidth, then you can do a bandwidth conversion that is between a traditional leakage detector IF bandwidth and the full 6 megahertz roughly of the channel bandwidth. And you see that it's 20 something dB down, and see, wow, that's noise-like. It's not going to cause interference. And in fact, it can, because we, at one time in years past, turned my backyard into an antenna test range and had the engineers from the leak detector manufacturers and SCTE and a couple MSOs here. And we were doing testing and characterizing digital leakage, and found and showed very definitely that you can cause harmful interference when digital signals leak. And this right here says, despite the fact that SC-QAM signal power is spread out over most of that channel bandwidth, moderate to high power leaks or high field strength leaks rather, can cause harmful interference. And we proved that. We used some radio equipment, and there's a screenshot in the lower left of this slide that shows a ham radio transceiver signal level meter, and you can see here that that's just noise from a leaking signal. And it was a calibrated leak that we set up, but it's S9 plus 15 dB caused by a 400 microvolt per meter leak at 10 feet. And yeah, that's sufficient to be harmful interference. And then we look over at the right, we can see a display from, I think this came from the old Rodian Schwartz PR100, but basically a good spectrum monitor here. And here we can see, let me move this little guy out of the way just a bit. Here we can see leaking SC-QAM signals in the spectrum. And what do we see that's also here in the spectrum? Well, there's Verizon's LTE downlink coming from their tower, and there's some public safety two-way radio communication stuff over here, and then some more of the same type of stuff over here off to the right. But you can see there's leakage here, and if this is high enough, it can interfere with cellular operations, LTE operations, and who knows what else. So we need to pay attention, even in cable networks that are carrying all digital signals. So yes, leaking digital signals can cause harmful interference.
So does the FCC require cable operators that have all digital channels to do FCC proof of performance testing?
That's an interesting question, because if you look at the FCC rules in Part 76, there are rules that pertain to analog TV channels and doing proof of performance tests on them. There are rules that pertain to the performance, that is the signal quality of digital signals that are also in there. But the FCC doesn't actually say to include the digital signals in your proof of performance test. But I think it makes sense to go ahead and test them anyway, just to have that information on hand to make sure that the signal quality of your digital signals is at least in compliance with what's spelled out in Part 76 of the rules. And the reference is SCTE 40. So that's your signals in your network have got to be that good or better. They're supposed to be. So, and the reason I say you should make sure they are anyway, because if the FCC came to town and did a check on your system, they'd certainly want to see your public records and say, okay, you've been doing proofs on your analog channels if you have them. What about your digital signals? How are they playing? And you want to make sure that they're in good shape. And there are also signal leakage limits for analog and digital signals in Part 76, and it's specifically 76.605C. is the paragraph where there's a table that includes leakage field strength limits for analog and digital signals.
Yeah, and so that was going to be my follow-up, is should cable operators do the proof of performance testing, even if they're, technically not required? And I think you answered yes to that. And I'm using the FCC, that's for, the United States, but Canada, Europe, other countries also have their governing bodies that have requirements on how much plant leakage you can have, how many signals you can have leaking out of your coax cable, your amplifiers, that, to Ron's point, could be impacting communications, public safety, airplanes flying over our heads. So it does matter. We can interfere with other people the same way they can interfere with our network. So we do care.
And if you've got ingress, go fix the leak.
Yes.
You find out where that's getting in and fix it. It's your responsibility. It's not the fault of the ham operator. I'm a ham operator. I can legally transmit with up to 1,500 watts. And if my antenna is 50 feet from a loose F connector on the next door neighbor's house, whose fault is that?
Yeah, it's not your fault.
It's not mine. I'm legally authorized and licensed to transmit with that kind of power. The problem is that loose F connector. It's not the
tighten those connectors, folks.
Yes, and whatever else is causing leakage. All right, and signal leakage in a digital network. Did you know that the older legacy detectors cannot be used to measure digital signals? They're only compatible with a modulated analog visual carrier or a CW carrier. When we were doing that digital leakage characterization, we had some of the old style analog only leak detectors, and of course they gave bogus readings because their detector circuits were optimized for a CW carrier or a modulated visual carrier. They just saw the QAM signal as noise and didn't respond to it. Of course, all the leak detectors available today are in fact compatible with that. So that's the good news, that all the leak detector manufacturers have got digital compatible leakage detection equipment. And in most cases, those detectors operate over multiple frequencies. So you can test for leakage down around the VHF aeronautical band and up in the higher frequencies in the UHF spectrum where LTE and other services hang out. So,
yeah, and I'd just like to take a moment to plug leakage detectors. I'm such a big advocate of leakage detectors, both in the outside plant and also pressure detection for inside wiring. They work so well with proactive network maintenance. Of course, I'm a huge proponent of proactive network maintenance, so thank you. Anytime we find like impedance mismatches, so loose connectors, corroded connectors, anything like that in the outside plant with correlation groups, the quickest way to troubleshoot that, squirrel shoes, radio cracks in cables, you will find that very quickly with leakage equipment. And then similarly, like in-home wiring, when you're trying to troubleshoot in-home wiring as a tech, loose connectors, any kind of compromised shielding, where you have maybe a crack on a drop or a loose connector on a drop, the quickest way to find that is with a pressure test kit. And so I really recommend that. It can really reduce your time as a maintenance tech or an in-home tech that you're doing troubleshooting, that type of stuff. If you have a leak in your plant, leakage detection will take you immediately to where that leak is and really help you reduce your time to try to find these type of problems. So strongly recommend that equipment. It helps you out.
Yes.
Any vendor, get their equipment if you don't already have it. And if you have it, just use it.
Yes. And a bit of a spoiler alert, our next two presentations or next two sessions are about ingress.
Yes.
And of course, the mechanisms that cause ingress are the same ones that cause leakage.
Yes, and Jeremiah also talks about flyover. So there are people that do that basically get into planes or drones, helicopters, and they do flyovers in plants. And so he's saying CLI flyover checks and FCC standards need an update. Not many changes in the last 20 years to mention these digital sources.
Actually, the FCC rules were updated just a few years ago to take into account digital signals and digital leakage. So yes, awesome. They were updated. Right. I was one of the subject matter experts that got involved behind the scenes in some of that activity that led to the new rules.
Great. Thank you for the update, Ron.
Yes. All right. And most of those, getting back to the new leakage detectors that are compatible with all digital networks and multiple frequencies, most of those operate by injecting a low-level test signal in between adjacent SC-QAM signals, typically 20 to 30 dB down, give or take. And then the leakage detector is actually monitoring for those special test signals in between the adjacent QAM signals. And then it applies an offset. So let's say the leakage test signal is 30 dB below the power of the SC-QAM signal. Then the leak detector actually measures the field strength of the test signal and then applies a correction factor of 30 dB so that the displayed field strength is equivalent to what it would be if it had measured the actual SC-QAM signal itself. Okay, now here's a fun one that I love to give people some grief about because we hear people say, "Oh, I've got I've got interference on EIA channel 32," and I say, "No, you don't. There is no EIA channel anymore."
I still say EIA channels.
Yes, I know.
So you're going to give me grief on this one.
I'm going to give you grief about this too. Did you know the 6 megahertz wide channel designation in our cable networks, and this is networks that carry 6 megahertz space channels, is defined in an international standard that is maintained by the Consumer Technology Association. That standard number is CTA 542D S2023. That's the latest version of it, and the title is Cable Television Channel Identification Plan. Now, in the past, the channel plans on our networks had different names and designations depending on when. But it was IS6, which was interim standard 6, the NCTA channel plan, the NCTA/EIA channel plan, the EIA channel plan, and that's the one most people remember. Yeah. Then the EIA/CEA channel plan, because the Consumer Electronics Association took over the channel plan from the EIA, and then when the CEA changed its name from the Consumer Electronics Association to the Consumer Technology Association, the name of the standard changed, and of course the name of the channel type changed. So they are now CTA channels. For those who are curious about the old EIA designation, that designation was replaced about 20 years ago by the CEA channel plan. So
I'm going to catch up soon, Ron, I promise.
20 years, yeah, just 20 years. So they are CTA channels. CTA channels. Okay, let's talk about UHF TV Ingress. Did you know that when an over-the-air UHF broadcast TV channel, whether it's analog or digital, leaks into a cable network, good old ingress, it can interfere with 2 cable channels. And the reason is there's a 2 megahertz overlap or offset between North American over-the-air UHF TV channel slots and the North American standard and IRC cable channel slots in the CTA plan. And if you look at that CTA standard, it has the channel plan for standard channelization, for IRC, which is incremental related carrier, and HRC, which is harmonic related carrier. But you can see the offset down below. So the upper row shows the UHF broadcast channel lineup, numbers 14, 15, 16, and so on. And then right underneath it is the cable channel plan, the CTA channel plan, and you'll note that there's a 2 megahertz offset. So let's say UHF TV channel 14 is leaking into the cable network, and it doesn't matter if it's digital or analog. It leaks in, it's going to interfere with cable channel 65 and 66 as an example.
So that also means it's DOCSIS channels that will impact as well. It's not just video.
Well, yeah, if that's UHF broadcast ingress and you happen to have DOCSIS channels there, it's going to hammer 2 of them rather than just 1. Now, here's an interesting thing. The over-the-air and cable VHF channel slots use the same allocation. So, for example, here I show the VHF high band. I've got over-the-air VHF channel 7 through, well, I only go up to channel 11 here. But cable VHF 7 through 11, and you can see that the channel slots are on the same lineup. Hold on just a second.
No problem, Ron.
I'm doing a live thing, and don't worry about it.
It's all part of the show.
Doorbell rang. Yeah. At least Denise isn't bringing me lunch today.
That's flavor.
Oh, goody. It's a package that was just delivered. I like that.
Hopefully it's something exciting, like more ham radio or telescope equipment.
No, I didn't order anything. It's probably
too bad.
Food. Anyway, all right, let's get back to the business at hand here. Did you know that most older amplifier, and by the older I mean from way back when, automatic gain control or AGC circuits in those old amplifiers don't work well with digital signals on the AGC pilot frequency?
I just had a question from a customer on this recently, so I'm really glad you're getting into this.
Well, and the reason is the older AGC circuits, and this is, again, it's the older AGC circuits, not the newer ones, were originally designed for analog TV channels or CW carriers, for the visual carrier or the CW carrier, not for noise like digital signals. And typically the AGC circuit had a bandpass filter in it that was tuned around the visual carrier frequency of analog channels, and it might be a megahertz or wide, whatever the design was in the manufacturer's product. And so it wouldn't really respond accurately to a noise-like signal in that same place. But in the last, I'll call it probably couple decades, most of the amplifier manufacturers, of course, changed their AGC circuit design so they have digital compatible AGC. But again, many of those older amps don't. So here's a screenshot. This was actually taken from my own subscriber drop. And here you can see an AGC pilot CW carrier at 499 megahertz for older amplifiers in the node service area where I live. Now I have to go back and check. They may have taken that out because they've been doing some upgrades in the node, and they may have replaced all the amplifiers with amplifiers that have the newer AGC circuits in them. So if you've got those really old amplifiers, you've got to keep a CW carrier on there for the best performance of your AGC if you want things to work right, and that's why this one was there. So otherwise. Check and make sure that you've got the correct AGC circuitry for the signals that are being used for AGC pilots in your cable network.
Yeah. So I'll come back to this in a minute. I just want to, Jeremiah mentions, he says, nothing beats PLN ingress, can be tough to track and affects the most spectrum when present. Are you familiar with PLN? Power line ingress. Okay, yes. So yeah, that is nasty.
And that's what that is that's usually something called power line gap noise. I am part of an IEEE working group that is just about finished with a recommended practice on power line gap noise. We've been working on this for several years, and it just went through the ballot process at IEEE, came back with some questions and some suggested changes. So we're in a group that is, or I'm in the group that's been working on that to make the suggested tweaks. and we're also working with the IEEE to make sure that we get the tweaks the way they're supposed to be. And then that document should be available soon. Hopefully it's soon. I think IEEE sells their recommended practices, but power line gap noise is probably the biggest source of power line type interference that can get into our cable networks. And you can't blame the power company because that happens in their plant, but you want to make sure your plant's good and really, really tight. But gap noise occurs when you've got metallic components, pole hardware, staples around ground wires, nuts and bolts on cross arms, those things. When they're up closer to the power line and they're inside the field that surrounds the power line, that field can induce current in those metal components. And let's say you've got a loose staple on a ground wire on the pole, got a little gap there, and it'll actually spark. And that sparking creates electrical interference, and it can generate interference over a wide frequency range, and it's real nasty. A lot of people like to use an AM radio to try to track it down. The downside to that is at the low frequencies where the AM broadcast band is, that stuff can propagate long distances. The closer you get to the source of the gap noise, the higher frequency can be heard. I've used some of my 70 centimeter ham radio equipment, which is up in the 450 megahertz range. And you get right underneath the source of it on the pole, at the pole. It is receivable there. And then the farther away of course you can't hear it at those higher frequencies. But that's a nasty one to track down. It can cause interference if you've got any place where that can get into the plant.
Yeah, so I'm actually glad Jeremiah brought it up, and I'm glad you explained it, because this is a bonus, did you know, in here, power line gap noise. I thought I understood power line gap noise. I thought it was just like arcing on the power lines until it was probably maybe a year ago. You and I were talking about it on a Cable Labs call, and you described it to me. How it can be just a couple pieces, like you said, a couple of staples on a power line where you get that arcing.
On the ground wire.
Yes. So I was shocked by it. I thought I understood it as completely different. So really disruptive and in a place where I wasn't looking for it. So thanks. Another bonus, did you know?
Yeah, some people mistakenly think that it's caused by corona discharge on high voltage lines.
That was also me. Yeah, it was me.
No, that generally does not cause that kind of noise and interference. We've got a 230,000 volt transmission line, not too far from a couple miles away from us, and that you don't hear anything on the radio till you get right underneath it. But if you've got loose hardware on poles, that loose nuts, and you got a little gap between a washer and a nut, that can be the source of gap noise. Fun stuff.
So, and one follow-up to the AGC, for operators that are looking at migrating to distributed access architecture, where they're using RPDs, that's something where you want to make sure that you are kind of considering how you're going to supply a signal to those AGCs. Because right now you may have a pilot signal that you're running from your head end. You want to make sure that you're working with your RPD vendor, that either that RPD is going to supply the pilot tone to your AGCs and it's going to be in the right frequency, or if your amplifiers are newer amplifiers, then they can just use, as Ron was mentioning, they can use the QAM channels that are coming out of your RPD to provide the power to your AGCs that are going to use then for the automatic gain control.
That's a good point, Brady. The RPDs are supposed to be able to generate CW carriers.
Correct.
To be used for call it legacy leakage measurements, or to simulate the leakage test, the proprietary leakage test signals, or AGC pilots. And I can't remember the number, but I used to be on I think it was the Cable Labs working group that was creating some of the specs, and I think, and I'm going by memory here, I think it had to support 5 CW carriers.
I believe it's 5, yeah.
Yeah, and then you configure those when you configure the RPD, and you can configure for an AGC pilot, for a leakage test signal, or whatever. All right, let's go on to single carrier QAM signal carrier to noise ratio. And we've talked about this one before too, but I want to reemphasize it here. Did you know, when using a spectrum analyzer or a similar spectrum monitoring instrument to measure the carrier to noise ratio of a single carrier QAM channel or signal, the carrier to noise ratio is simply the signal's height above the noise floor in dB, just like that. Now, need to emphasize, and we talked about this before, make sure that the spectrum analyzer is displaying the cable network's noise floor, not the test equipment's noise floor. So here you can see the height of the haystack above the noise floor is about 15 dB. And the way you make sure that your noise floor that's on the test equipment is the system noise floor and not your test equipment noise floor is you temporarily disconnect the RF input from the spectrum analyzer, and that noise floor better drop 10 dB or more. If it drops less than that or doesn't drop, the noise floor you're seeing is the test equipment noise floor, not the cable network's noise floor. Oh, and this is an interesting one here. Moving into AM fiber links. We still got a lot of these out there, although as people migrate to distributed access architectures, the AM fiber links are being converted to digital links, typically Ethernet based. But did you know, and we assume that an optical fiber link, it's an AM fiber link, is operating within its linear range, a 1 dB change in signal level at the input, that's the RF input, to the optical transmitter will result in a 1 dB change in signal level at the optical receiver's RF output. So here's an example. Let's say we've got a fiber link, and at the input to the transmitter, the per channel power is 15 dBmV. We've got minus 10 dBm optical input to the receiver, and the output of the receiver is 20 dBmV. So you crank up the input by 1 dB to 16 dBmV at the transmitter. The output of the receiver goes up 1 dB from 20 to 21 dBmV. Note that the optical level didn't change, and the average optical power will stay the same as long as the optical modulation index is correct. That is in the 0 to 100% range. Now this one is a little bit different, and this is where there's some confusion. Let me move this guy up here. A 1 dB change in optical power. Now we're not talking about the RF signal level, but the optical power at the input to the optical receiver will cause a 2 dB change in signal level at the receiver's output. So let's say we've got the same thing as before. We've got 15 dBmV input to the transmitter. We have minus 10 dBm optical input to the receiver, which gives us our 20 dBmV output at the receiver. But if we do something, let's say that increases the optical attenuation in the fiber by 1 dB. So now notice the RF input didn't change at the transmitter. What did change is the optical power. So it goes from minus 10 dBm to minus 11 dBm.
So maybe we kink that fiber just a little bit.
Yeah, you kink it. You could do it that way, or a really bad splice, or a dirty mechanical splice. The RF output goes from 20 dBmV to 18 dBmV. So it's a 2 dB change. And you say, wait a minute, what is going on here? Well, did you know that 1 dB optical power versus 2 dB RF power relationship in those analog AM fiber links is not, because of this old myth that we seem to see a lot of or hear a lot of, optical decibels are twice as big as RF decibels? No, they are not. This is from the book Modern Cable Television Technology, 2nd edition. This explains what's going on. And I will read this to you, so hopefully there's no confusion about it. Optical transmitters and receivers are not linear devices, but rather are square law devices. That is, the instantaneous light output power of a transmitter is proportional to the input current and thus to the square root of the input signal power. At the other end of the circuit, the RF output power from the detector is proportional to the square of the optical power received, so the total link is nominally linear. Now, there's pre-distortion that's often used to overcome some hanging around nonlinearities or residual nonlinearities. However, the square law transfer function has an effect on noise and distortion in particular because of the square law detector transfer function, a change of 1 dB in optical loss power, leading to that commonly stated but incorrect statement that optical decibels are twice as big as RF decibels. So now you know the rest of the story.
So optical dBs are not as big as RF dBs.
They're the same. They're the same.
A dB is a dB.
That's right. They're all ratios. All right. Now let's talk a little bit about frequency response. Did you know that the broadband sweep gear we use to align and maintain our amplifiers and sometimes nodes only shows half of the measured response? And you say, well, wait, what do you mean half? Just the upstream or the downstream? And to say half is maybe a little confusing. That's probably not the right word, but a sweep display only shows one part of the complete frequency response, or more accurately, the complex frequency response.
I'm phasing out of this conversation.
What's that?
I'm phasing out of this conversation, Ron.
Oh, no, don't phase out here. Let's see. You're just going through a phase. That's all.
Yes.
Frequency response is a complex quantity that has two components: magnitude or amplitude versus frequency, and phase versus frequency. Our sweep gear doesn't show the phase versus frequency part of it. So what you see here on this display is what you might see in this upper circled red part here on a typical sweep receiver. You can see the amplitude versus frequency response across the return path. But this kind of sawtooth pattern down below it is the phase versus frequency response. Now it looks like this sawtooth pattern. That's so you can see it all on one display. But if you took all these and kind of glued them together and what you'd wind up with is a big, long, sloped line that represents phase versus frequency in degrees. And so the display of a conventional broadband sweep receiver shows us amplitude versus frequency, but not phase versus frequency. And here's an example of upstream sweep and the response up to, in this case, 35 megahertz. You can tell that's an old one. I think that came off of a KLAN receiver.
Yeah, and I think where we really get concerned about phase is close to the diplex filter, or close to the band edge. And in most cases, is that correct?
Well, take a look here. If you look at this phase line here, on most of these, the phase line is nice and straight.
Right.
But as you get close to the edges, notice that the phase line,
it's inconsistent there.
A little curve there to it. And when you translate that to group delay, there's a mathematical formula to do that, you get this group delay curve like you see here. And in this case, we see group delay in time in the vertical axis. So vertical axis is time, and the horizontal axis is frequency. You get this so-called bathtub curve here.
Right.
So the group delay is really nasty here between 5 and 10 megahertz, and it's really nasty from 35 to 42 megahertz. But not much group delay going on down here.
Correct.
This vertical scale is 100 nanoseconds per division. So if you pop a signal up here between 35 and 40 megahertz, you've got so a couple divisions, you've got 200 nanoseconds of group delay in that channel between 35 and 40 megahertz. And what that means is it takes longer for part of the signal to get to the destination than another part of the signal. So different parts of the signal or different frequencies are traveling in different amounts of time. That's what group delay is. And that can raise Cain with digital signals.
Particularly DOCSIS signals, when the modem's transmitting to the CMTS, that causes the CMTS a challenge to demodulate those signals coming from the modem.
If pre-equalization is not used.
Correct.
Thank goodness we have pre-equalization in the upstream and equalization in the downstream, because that will compensate for the presence of group delay distortion.
Absolutely.
All right, so ideally then, amplitude versus frequency should be flat. That's what we want to get when we're sweeping our gear. And the phase should change in proportion to frequency. Remember those nice flat lines? Well, they were sloped, but nice linear looking lines. So when amplitude versus frequency is not flat, we see amplitude ripple, what some people call standing waves or tilt or suckouts or other response impairments. But when phase versus frequency is out of whack, we have group delay distortion. So here's a fun one. We're kind of in between the seasons of what are called solar transit outages. These typically happen in the March and October timeframe. But did you know that what are sometimes called sunspot outages have nothing to do with sunspots? There's a bunch of sunspots on the sun right now, but they don't cause any problem, at least not with respect to these solar transit outages. So this has nothing to do with sunspots. They're actually solar transit outages. Some people call it sun fade or sun outages, and they happen twice yearly, typically March and October, when the sun lines up behind geostationary satellites. So think of the sun as this great big radio transmitter. It's transmitting radio signals, and it's actually transmitting energy over the entire electromagnetic spectrum. But you get the sun right behind a satellite. The dish on the ground is receiving a weak signal from the satellite, and it's also receiving this noisy interference from the sun. So we get these solar transit outages. And that's something that we've had to put up with ever since we've started to carry satellite signals on our networks, going all the way back to the mid-'70s.
Huh, that's interesting. It's completely the opposite of what I thought the solar outages were through. I thought they're like big solar flares that were interfering with them. So
no, you get big solar flares, and that can cause a radio blackout in the shortwave radio spectrum over the air. And the fact that's going on, right now there's a bunch of sunspots on the sun. I'm one of my hobbies is astronomy, and I have a telescope in the living room behind me, and I'll pop a solar filter on it and take it outside when the sun is shining and look at the spots. And there's some spots on there that are bigger than Earth, and they've been coughing up flares sometimes 2 or 3 times a day for the last, several weeks. We're on the uphill side of the sunspot cycle, 11-year solar cycle. But no, that doesn't cause our solar transit outages with our satellite dishes. It happens when the sun lines up right behind the dish, right behind the satellite, and then our dish is looking at the sun and the satellite. And sometimes the RF power from the sun can actually overwhelm the weak signals coming from the satellite. So we have an outage. We don't get anything.
So cool. When Jeremiah says that they shift feeds from differing master head ends to avoid most of these days. That's cool. I didn't know that either. I'm so glad I attend these shows. I learned so much on these.
That's a trick that's been done in more recent years, say the last 10, 20 years or so. But oh man, early days of satellite reception, we couldn't do anything about it because you'd have dishes at the head end, and all right, it's March and October, and then of course the CSRs in the office would tell the customers, it's sunspot outages. No, it's solar transit outages. But I guess that's easier for people to understand than solar transit outages. All right, so continuing. Reliability versus availability. Did you know that reliability and availability are not the same thing? Availability, by definition, is the ratio of time that a service, a device, or a network is available for use compared to total time, usually expressed as a percent of the total time. And reliability is the probability that a system or device will not fail during some specified period. So in addition to percent, availability is sometimes stated as some number of nines, and you probably have heard this, 4 nines availability or 5 nines availability or something like that. So for example, if we say 4 nines availability, we would express that as 99.99%. That means that a service is available 8,759.12 hours out of 8,760 hours in a year. So another way to look at it is, if you've got 4 nines availability, that on average, that service is going to be unavailable about 53 minutes per year. And if you talk about 5 nines availability, then you're talking about unavailability down around 5 minutes per year. So that's a tough one to get to, but it is doable with equipment. And a total power, this is a fun one, but did you know that a quick way to estimate the approximate total power is based on a rule of thumb that each time the number of channels doubles, and we assume that all the channels have the same signal level, the total power increases by 3 dB, or actually 3.01 dB. So for instance, if you've got one channel and the power per channel is 0 dBmV, the total power is 0 dBmV. If you double it to 2 channels, each at 0 dBmV, the total power goes up 3. So it's now 3 dBmV. You double from 2 to 4 channels, each one's at 0 dBmV, the total power is 6 dBmV. You go from 4 to 8 channels, each at 0 dBmV, it goes up 3 dB, now you're 9 dBmV, and so on. So you can see that it's a real simple rule of thumb. Each time you double the number of channels and you keep the per channel power level the same, then the total power goes up by 3 dB. Of course, if you're a math nut, you can also use this formula. So total power equals power per channel, so 0 dBmV in this example, plus 10 times the base 10 logarithm of n, where n is the number of channels.
Yes, so, but your channel your doubling is just so much easier to do than the formula.
And you'll be pretty close. And then, of course, SC-QAM signal amplitude ripple, what some people call standing waves, but technically it's the standing waves that cause amplitude ripple. But did you know a quick way to determine the approximate in-channel flatness of a single carrier QAM signal is to use a properly tweaked spectrum analyzer to observe the top of the haystack? So here I show a couple examples. On the left, it's an old 8591C spectrum analyzer display, and the vertical scale is 3 dB per division. And note that the top of the SC-QAM signal fits completely in there, so you can tell, all right, your peak to valley frequency response of that SC-QAM signal is less than 3 dB. This looks like it's probably closer to about 2 dB maybe. dB and a half. And then over here is a Sunrise Telecom box. Although looking at the graphic, that's even older. That's from
Avantron.
It was called Avantron, yeah. But here you can see the same thing. But here you can put you got to adjust resolution bandwidth and video bandwidth and stuff just right to the settings that are shown here. And then you take the markers in this case, and you can see the peak to valley frequency response of your SC-QAM signal. So in this case, it's a little over dB, about 1.2 dB peak to valley. So quick and dirty way to see what the approximate in-channel flatness is on your SC-QAM signal. Now let's talk about a fun one. This is a DOCSIS topic. Well, actually, it applies to DOCSIS and legacy digital video. But did you know that in the DOCSIS downstream, Reed-Solomon forward error correction, in fact, 7 bits equals 1 Reed-Solomon symbol, and 128 Reed-Solomon symbols equal 1 Reed-Solomon code word. So let's visualize this. So here we take 7 bits, so we got some zeros and ones, put those 7 bits together, and those 7 bits equal a single Reed-Solomon symbol. This is in the world of FEC now. Now, I said that 128 of these Reed-Solomon symbols, remember each one is 7 bits, equals 1 Reed-Solomon code word. Now, the slide wasn't wide enough, so when I created this graphic, I couldn't put 128 of these symbols, so I got some ... in there. But so the different colors represent different Reed-Solomon symbols. So we got the symbol number 1, number 2, number 3, 4, and so on, 127.
All the way to 128, yes.
All the way to 128. And that's one code word, one Reed-Solomon code word. So each Reed-Solomon code word has 122 Reed-Solomon symbols or data symbols, and 6 of those symbols are parity symbols. That's for the error correction function. So did you know that any number of bit errors in a Reed-Solomon symbol means the entire symbol is toast? So here we've got 7 bits in a Reed-Solomon symbol. They're all good, no errors. So this is a good symbol. What about when you have got just one broken bit in that 7-bit symbol? Well, it's considered errored. They might as well all be errored. You got 2 in there, same thing. It's considered an errored Reed-Solomon symbol. And of course, if they're all broken, it's still an errored Reed-Solomon symbol. So all these last 3 are basically treated the same way. They're all toast. The only good one is one with no bit errors at all in the symbol. So did you know that for a Reed-Solomon FEC configuration of what's called T equals 3, the FEC decoder in the receiver can fix up to any 3 errored symbols in a Reed-Solomon code word. So here's an example. Let's say you've got our 128 symbol Reed-Solomon code word. So this is one code word, and the 3 that I've got colored in red here are 3 errored Reed-Solomon symbol. And what that means is that the FEC can fix those 3 broken symbols, and now we have what's called a correctable code word error. The code word has been fixed and it's good, but it's called a correctable code word error. So when you see these correctable and uncorrectable counts, this is the correctable code word error. It means that it was fixed. However,
we also call that like pre-FEC, right? Or pre-BER on some
sort of. There's the math document I mentioned earlier, the SCTE 270-2021, has a discussion about that, and it mentions the fact, I think it's in the math document, that in the FEC it's not quite as straightforward as the pre-FEC and the FEC post-FEC stuff as most people think, and it's in a section on bit error ratio. But yeah, we often call that pre-FEC. All right, so did you know that when there are more than 3 errored code words or 3 errored symbols in a code word, the entire code word is junk? So here I show 4 errored symbols. So there's one there, there's one there, one there, one there. The rest are good. The entire thing is considered uncorrectable. So
now that whole packet of data is junk.
Yeah, that whole thing is junk because the FEC is configured for T equals 3. It can only fix up to 3 broken symbols in a code word. If you've got 4 or more, that code word is toast. Okay, continuing on, and here we get into the world of low density parity check, and I'm not going to talk about that because that is really nasty, gnarly, hard to understand stuff. But people will talk about this, and they're used to saying, well, look, if I've got pre-FEC bit errors and post-FEC bit errors on my SC-QAM signals, I need to go out and find out what's causing the prefec errors and fix them, because that means that I'm going to probably get a bunch of post-fec errors at some point down the road. So in the case of the way DOCSIS 3.1 and LDPC works, it's normal to see correctable code word errors in an OFDM signal. So don't be surprised if you see them. You might not always, but if you do, don't worry about it. So here, this is considered normal. You can see, got some correctable code word errors. But what don't you see?
Uncorrectables.
Uncorrectable code word errors. That's what's important. You do not want uncorrectable code word errors. In fact, you can have a scenario where if the carrier to noise ratio or the RxMER is within 6 dB of the failure threshold for the modulation order, it's pretty typical to see 100% correctable code word errors, and yet no uncorrectable errors. That again is normal.
Yep. So see it all the time.
Yeah, I see it all the time too, and I hear people saying, "We got to go find out why we've got these correctable code word errors in our OFDM signal." Ignore them. Do you have any uncorrectables? No. All right, don't worry about it.
No problem.
It's no problem. Okay, and almost to the end here. Did you know that full duplex DOCSIS or FDX DOCSIS allows downstream and upstream signals to simultaneously occupy the same frequencies? And you say, wait a minute,
how's that possible?
Yeah, how can you have downstream, whoops, didn't want to do that, downstream and upstream signals on the same frequency at the same time? And they don't interfere with each other. Well, you get away with that because of the magic of this thing called echo cancellation. There's some other things going on in DOCSIS 3.1 and 4.0, but it allows these downstream and upstream signals to simultaneously occupy the same frequency. So there's some cool stuff going on there that makes that possible. And it works. It really, really does work. So that takes me to just about the end here. So many topics, so little time. And did you know if you missed part one, you can find a recording on YouTube right here at this URL. And I think Brady had also posted it down below, so you should be able to see that. So
I did.
It's a good video and a fun video to watch. We had a fun time making that one. And that's it. So
that last show was great. This one was great. Great information. Peter Vittman, great to see you on the show again. Peter says, from my understanding, there's a difference for BER and CER on measurement devices. For real prefec BER, the tuner/FEC will tell the exact number of bits corrected, counting the entire code word, correct? So, Ron?
Well, now we're starting to get into I'll call it the DOCSIS things that I am definitely not an expert at. But you get into things like unreliable code words and some other things in DOCSIS 3.1. That might be a topic for another day, or maybe something you and John Downey can beat up on.
We'll get into the details of that. So, yes. Peter, we'll get that on another day, but I think you are
BER
correct,
is
Peter.
generally not something that's really of concern in the world of DOCSIS 3.1. You really need to pay attention to code word errors.
Yeah, and BER, bit error rate testing, is more of an invasive test where you inject a known number of data, and you have a receiver that receives that data. Yeah. So you know what you're transmitting, you know what you're receiving, and you basically count the bits that are errored on the receiver from what was transmitted.
Now the thing is, people will say, "Well, I've got legacy SC-QAM signals here, and I measure pre and post-fact BER with my meter. Is that really a true BER measurement?" The answer is no. Right. It's not, because
it's estimated.
It's estimated from what the forward error correction is doing. It's reasonably close. It's good enough for maintenance and troubleshooting and stuff. But if you want to do a lab grade BER measurement, you need a bit error ratio test set, and it's a very service disruptive measurement because you inject a pseudo random binary sequence. And the detector has to be able to either recreate that, or you have that sequence connected directly to the receiver. And then the receiver compares or counts bit by bit. Okay, this is good. And compare it to the original. This is good. And then it finds a bad one. This is bad, where the other one was good. And then it will give you a count of the broken bits. And then you get a true bit error ratio measurement out of that. Yep. But that's a difficult measurement.
Yeah, James Long, he says, wow, I'm late, but James, we're glad to have you here. Thanks you for joining. Peter, looking forward to Ingress. So yes, Ron, you mentioned we were going to do a couple shows on Ingress sessions. So that will be, he says also maybe talk about impulse noise. I think that would be pertinent to the Ingress talk, Ron. Ron, you also mentioned a couple of times now, you've mentioned Modern Cable Television, the second edition book. So I just kind of want to show people what the book looks like. A highly recommended book.
Good reference.
Sikora,
Good.
Farmer, Largo, and Adams were the authors.
That's Dave Large.
I'm sorry.
Dave Large.
Dard Large. Oh my God, sorry, yes.
Yeah. Want to borrow my reading glasses?
Yeah, I do. Well, I don't have my reading glasses on. That's why I read them wrong.
Walt Sikora, Jim Farmer, Dave Large, and Michael Adams did the second edition. And after that one, they did a subset of the authors did another one just on HFC stuff, and they took the chapters out of that book and put them in a new book and did a complete update on it, and then corrected a couple formulas and did some minor editing and stuff, but made an update. And I've got that one in my library too. It's also a great reference. But yeah, that's a good book everybody should have in their library.
Yeah, I mean it's a great reference if you need any topic related to our industry, like when you're looking for formulas and stuff like that. It's a nice book to have for reference. So James Long says, I've been trying to get some of my fellows on the team to join cable school with you guys. They're missing out. We'd love to have them join, so send them a link. Yeah. And then he says also he just bought that book on eBay or something. So great, James. Definitely a good reference.
Good book. And for those of you who don't have it, another good book with formulas in it is the math document I've referred to a couple times. You can download it for free from SCTE Standards download page. It's called SCTE 270 2021 R1. And that's a 425-page document that is full of mathematical formulas and examples of how to use them. And there's a good appendix that does a deep dive on some of the topics. I keep that PDF copy of that on my desktop all the time, and I refer to it frequently because it's got about almost all the formulas you can think of for just about everything in cable. There's a few things we didn't include in that when we put it together, but it's a great reference too.
Ron, if you can remember to shoot me a link for that, I'll be sure to put that in the show notes as well. I know I have it somewhere, but
SCTE.org, and then you just click on standards, and then you'll get the drop-down menu, and that'll take you to the standards download page. And you open that page up and just scroll down to SCTE 270-2021 and click on it, and you can download the PDF.
I'll dig that up and I'll put it in the notes this weekend. So it'll be
Sounds good.
All right, everyone. I think that is a wrap on today's show. We hope you enjoyed everything, Ron, all the great information that Ron has provided us today. I learned a few things along the way once again, so thank you so much, Ron. Please don't forget to subscribe to our channel so you get the content when it comes out. Hit that notification bell. Please do drop your comments below. Let us know what you thought. Let us know what you'd like to hear coming up. Be sure to tune in on August 4th when John Downey and I will be back for episode 93. We're nearing 100 episodes with John and I. Ron, thank you again for the great information. We look forward to having you visit us again soon. We'll be talking about impulse noise. I think Mia has something to say.
Well, Ingress.
Ingress, yes.
Talking about
Ingress. Impulse noise is just one type of ingress. There's all kinds of ingress.
No, I was just going to say you might want to mention the show coming up.
Oh, yeah. So I will be at the Independent show in Minneapolis. The end, it's a first week in August, I believe. So
no, it's the last week of July.
Okay. If you know where the Independent show is, I'll be there. So love to see you there. If you're at the Independent show, please look me up. And then I think Ron and I will be at the Expo. So that'll be the next time show we're at.
Be presenting a paper at Cable Tech Expo this year.
Yep. So, all right. Again, Ron, thank you. Thanks for everyone who joined in live. We appreciate your comments. Until next time, take care. Keep learning, everyone. So, thanks again.